Adiabatic process. A process in which no heat is transferred into or out of the system is known as adiabatic process. In other words, we can say that the system is insulated from the surrounding so that no heat is absorbed or released from the system. In order to explain this, let us consider the picture. So here is my diagram where you can see I am using x-axis to represent the volume and y-axis to represent the pressure. And as you can see, I have two isothermal curves and two adiabatic curves over here, where in isothermal process the temperature does not change, and in adiabatic process the heat does not enter or leave the system. Then we can write for an adiabatic process V to the power gamma is equals to constant, where gamma is the ratio of specific heat at constant pressure and at constant volume, which is defined as gamma is equal to Cp over Cv. Now let us consider an ideal gas adiabatically changes from P1V1 to P2V2, then P1V1 to the power gamma is equal to P2V2 to the power gamma, because the gas is changing from P1V1 to P2V2 and gamma is the ratio of Cp over Cv. So basically we can say that the reason why we are writing this term because PV to the power gamma is constant. Let the work done by an ideal gas adiabatically from state P1V1T1 to state P2V2T2 is given as W is equal to integration from V1 to V2 P dV. And if we substitute the value, we will write P is equals to constant over V to the power gamma in this equation. So we will write W is equal to integration from V1 to V2 constant over V to the power gamma dV. When we integrate, we need to take the constant out and we need to take the denominator to the numerator. And if we do that, we will write W is equal to constant integration from V1 to V2 V to the power negative gamma dV, because constant should go out and V to the power gamma should go to the numerator, and that's how we got V to the power negative gamma. If we integrate, we will write W is equal to constant inside the bracket V to the power negative gamma plus 1 over negative gamma plus 1, and our lower limit is V1 and the upper limit is V2. Now let's substitute the lower and the upper limit and take this constant term out, which is negative gamma plus 1. So if we take that out, this is in the denominator. So we will write constant over 1 minus gamma outside, and inside the bracket I have 1 over V to the power gamma minus 1 from V1 to V2. And what we are doing, we are taking the numerator to the denominator. Now let's substitute the lower and the upper limit, and if we do that, we will write W is equals to constant over 1 minus gamma inside the bracket 1 over V2 to the power gamma minus 1 minus 1 over V1 to the power gamma minus 1. Now as we know that P1 V1 to the power gamma is equal to P2 V2 to the power gamma, and that is equal to constant. So basically for constant we are going to substitute these values, and if we do that, we will write W is equal to 1 over 1 minus gamma, and my first constant is P2 V2 to the power gamma over V2 gamma minus 1 minus P1 V1 to the power gamma over V1 to the power gamma minus 1. And the reason why I'm taking P2 V2 gamma here, because I have V2 in the denominator and the second term I have V1, so I should take the term with P1 V1, which is over here. Now if we simplify further, we will write W is equal to 1 over 1 minus gamma P2 V2 minus P1 V1, because we will cancel terms out here and here, and only term left will be P2 V2 minus P1 V1. Since we know that PV is equal to nRT, so we can write W is equal to 1 over 1 minus gamma, and for P2 V2 we can write nRT2 minus, for P1 V1 I can write nRT1. And as you can see, nR is constant, so we will take that out and we will write W is equal to nR over 1 minus gamma, and inside the bracket I have T2 minus T1. And this is how we will find the work done for an adiabatic process.